we have seen what unions and intersections of sets are. Another way of constructing new sets out of old is called the Cartesian product. Named after the French mathematician and philosopher René Descartes. So, if you have two sets S and T, then the Cartesian product is usually denoted as S times T. So, it is like a multiplication for sets, and an element of the Cartesian product is a pair, it is an ordered pair x comma y, where x belongs to S and y belongs to T. Why is it called the Cartesian product? Well, you have probably heard of Cartesian coordinates, right. So, when we want to represent points in the two dimensional plane, they have an x coordinate and a y coordinate. So, the plane, the two dimensional plane is the Cartesian product of real numbers cross real numbers, because it is just its points are just x comma y, where x and y are both real numbers. The final set construction that we are going to look at today is the complement. So, if S and T are two sets, then the complement of T inside S. So, it is usually denoted, it is like a subtraction of sets, it is denoted S minus T. It is called, let me write it down, the complement of T in S. So, I have to give you a rule for when an element x is in S minus T, and the rule is x belongs to S minus T if x belongs to S, but x does not belong to T. Those elements of S which are not in T are elements of S minus T. So, let us look at, for example, our favorite two sets that we had, S2, which is even numbers. So, that is 2, 4, 6, 8 and so on, and we have S3 multiples of 3, 3, 6, 9, 12 and so on. What is S2 minus S3? So, we are asking for those numbers which are even, but are not multiples of 3. So, let us go down the even numbers and see which ones are multiples of 3, those we do not list. So, we get 2, 4, well 6 is a multiple of 3. So, 6 is not in S2 minus S3. The rule is x is in S2, but x is not in S3. So, 6 is not there, then 8, 10. Now, 12 again is a multiple of 3. So, we leave it out, and then we go on 14, 16, 18 is left out and so on. So, we take multiples, even numbers that are not multiples of 3 is S2 minus S3. I will let you think about what is S3 minus S2. Having developed the language of sets, we are now ready to talk about functions. Functions are gadgets that are used to relate different sets. So, if you have two sets S and T, then a function f from S to T, it associates to each element of S an element, a unique element f of x, an element of T. So, visually you can think of it as you have the set S, you have the set T, and what the function does is it takes each point in S and gives you a point f of x in t. It does this for every point in x. Maybe the best way to understand this is to have some examples. So, in physics we come across a lot of functions when we try to study physical systems. So, in physics we often study functions of time. For example, you may be studying the motion of a projectile, and what you are interested in is the x coordinate and the y coordinate of the projectile at any given point of time. So, a typical function in physics is f of t somehow measures the state of the system at time t. It could be, the state could be position, it could be momentum, it could be temperature, velocity, whatever you like. Okay. In computer science, well, you all know what functions are, right. When you learn any programming language, you have to define, you learn to define functions. And what does the function do? Well, it takes an input, which is usually a data type, and gives you an output, which is another data type. So, in computer science, functions are the sets are data types, and functions are the functions that I have defined here in terms of set theory are the same as the kind of functions that you define in a programming language. So, here functions are defined by algorithms. For example, you might write a function to find the larger of two numbers. Suppose these are natural numbers, then you would write a function max to go from n squared to n, given a natural number x, a pair of natural numbers x comma y, it will give you, that would be the input, and the output would be the larger of x and y. And you would write this using cases: if x is greater than or equal to y, return x, otherwise return y. Sometimes functions are just given by formulas. So, in algebra, you may give a function by a formula: f of x is x squared minus x minus 1. You can think of this as a function. So, you need, so here I am being a little careless, what is s and what is t, right. So, I could take s, I could take this f to be a function from natural numbers to natural numbers, or if I want, I can take it as a function from real numbers to real numbers. And so there's some amount of choice here when a function is given by a formula, what is s and what is t. Okay, so these sets S and T have names. The set S is called the domain. What kind of input does your function take? And the set T is called the codomain. What kind of output does your function give? So, sometimes the function may be specified clearly without specifying the domain and codomain. And then we have seen some more functions already in some of our earlier lectures when we talked about sequences. Every sequence can be regarded as a function. So, we had looked at sequences of integers, we had the sequence of triangular numbers. So, we had the sequence 1, 3, 6, 10, 15. I am sure you all know what I am talking about here. T n is n into n plus 1 by 2, the nth triangular number. So, here this T n, n goes to T n is a function. So, t can be regarded as a function from natural numbers to natural numbers. Every sequence is a function with domain natural numbers. The manager of the Hilbert Hotel has a register in which he maintains a function where he has to keep track of the guest who is staying in each room. That is a function from natural numbers to the set of, well, the infinite set of all guests. The behavior of a function can change considerably depending on what we take to be its domain or its codomain. Let us consider the very simple function f of x is x squared. So, this is one of those functions that is just given by a formula, okay, it is a polynomial function. Now, I want to think of it firstly, let us think of it as a function from n natural numbers to natural numbers. Okay. Now, let me ask you what are the possible values of this function, right. Not every natural number is a value of this function, not every natural number is of the form x squared for some natural number x, right. So, what are the values? The values are the square numbers, the perfect squares. So, f of 1 is 1, f of 2 is 4, f of 3 is 9. Not all values are taken by this function. But if we look at this as a function from positive real numbers to positive real numbers, so I will use r plus, some of you may be familiar with this as the interval 0 comma infinity. So, r plus, this is also the set of all, let us use our set theory notation which you have just learnt, all the real numbers such that x is greater than or equal to 0. So, if I think of f as a function from r plus to r plus, then every positive real number, it is a fact that every positive real number has a square root, and so every value in r plus is taken by this function. So, every x, well, maybe I will call it y in r plus is a value of f. And finally, let me think of f as a function from r to r plus. Then every y in x r plus is a value of f at two different points. For example, 4 is 2 squared, but it is also minus 2 squared. So, this is a value of f in more than one way, in maybe two ways. 0 is only the square of 0, but any non-zero number is the square of two real numbers. Every positive real number is the square of two numbers, square root x and negative square root of x. So, in up to two ways. So, we have names for these different kinds of behaviors. So, firstly we can talk about injective functions. So, what this means is that if x and y are in S and f of x is equal to f of y, then x is equal to y. So, distinct elements, the function takes distinct values at distinct elements. So, which of these manifestations of x goes to x square are injective? Well, distinct natural numbers have distinct squares, right. If you have two different natural numbers, because they are both positive, their squares will actually be different. So, this is injective. What about here? when I look at it as a function from r plus to r plus, well, again if we have distinct positive real numbers, then their squares will be distinct. So, this function is also injective. But if we look at x goes to x squared as a function from reals to positive reals, then this is not injective, because for example, f of minus 1 is equal to f of 1. So, this is not injective. Okay, the next kind of function that I want to talk about is a surjective function. A function is said f is surjective if every element of the codomain is a value of the function. Meaning that there is some element, there exists x in S such that f of x is equal to y. Let us go back and look at our examples and see which of these are surjective functions. So, if we take the domain to be the natural numbers, then not every natural number is the square of a natural number. For example, 2 is not the square of any natural number. So, this is not surjective. What about f from r plus to r plus? Every positive real number has a square root. I have already pointed this out. So, this is surjective, and if I look at it as a function from r to r plus, well, it is still surjective. Now, we can put these two notions together and talk about bijective functions. Bijective just means that it is surjective and injective. In our examples, we see that x goes to x squared as a function from n to n is not a bijection, because it is injective but not surjective. From r plus to r plus, it is a bijection because it is both injective and surjective. From r to r plus, well, it is surjective but not injective. So, once again it is not a bijection. Let us look at some special subsets of the natural numbers. For each positive integer n, well, each n in n, I will use box n to define the set of the first n natural numbers. Okay, another way to specify this set is to say x in n such that 1 is less than or equal to x is less than or equal to n. Now, this set has just n elements from 1 to n, and it is convenient to say that 0 is just the empty set. A set is said to have cardinality n. A set, let us call it S, has cardinality n. This is just a fancy word for saying the set has n elements if there is a bijection f from n to S. So, for example, the set one, 2, 4, what is its cardinality? It has cardinality 3, because there is a bijection from the set 1, 2, 3 to this set. You just take 1 to 1, 2 to 2 and 3 to 4. Okay, so, if a set has cardinality n, then it is a finite set, if it is a cardinality n for some natural number n. Infinite sets can be rather peculiar, and this is one of the things that Hilbert wanted to illustrate when he came up with the example of the Hilbert Hotel. So, let us look at the set n union 0, this will be my domain, and my codomain will just be the set of natural numbers. There is a bijection from n union 0 to n, even though this is actually a larger set. What is the bijection? You just take each element x here to x plus 1. I can show you pictorially. So, you have the, well, you can think of this as the corridor of the Hilbert Hotel, and then you have the rooms 1, 2, 3, 4 and so on, and then you add a new room called 0, or this you could think of as the person who comes into the hotel looking for the room when the hotel is already full. So, now you have the original people who are living in the Hilbert Hotel, and you have this one more element called 0, and this function n goes to n plus 1 is simply taking this element and putting it here, this here, shifting to the right on the number line by 1 unit. And since the number line extends infinitely towards the right, this process is always possible, and this gives a bijection from n union 0 to n. So, what seems paradoxical here is that a set is in bijection with a proper subset. There is a bijection from a set to a proper subset. You do not see this with finite sets. The set 1, 2, 4 cannot be in bijection with any proper subset, because this has 3 elements and a proper subset would have less than 3 elements. But natural numbers union 0, well, this has infinitely many elements, and natural numbers, well, that also has infinitely many elements, and in this case it is possible to find a bijection from natural numbers union 0 to natural numbers. There is no paradox here, this is just how infinity works. In set theory, we have a notion of the size of a set, or we try to say how many elements does a set contain. We call this the cardinality of a set. For finite sets, the cardinality of the set is basically obtained by counting the number of elements in the set. Look, for example, at this set of jewels that I have here on the table. How many are there? I could just count them. So, I would count them 1, 2, 3, 4, 5, 6, 7, 8. So, I have 8 jewels. What have I done here? I have constructed a bijection from the set of a set of natural numbers 1 to 8 to the set of jewels. So, we would say that a set has cardinality n if there is a bijection from the set of the first n integers onto the given set. Similarly, we can ask when two sets have the same size. So, two sets have the same size if there is a bijection from one set onto the other. So, here for example, I have the set of all jewels and I have this set of sticks. Now, we could ask, do these two sets have the same size? And what I could try to do is make a bijection from this set to the other and see if I am able to do that or not. So, first I would take one of these sticks and pair it up with this jewel. Then I would take the second stick and pair it up with the second jewel. I would take another stick, pair it up with another jewel, another stick, pair it up with another jewel, and so on. Can I pair every stick with a jewel? You see, I have paired each stick with a jewel, and this is essentially a bijection from the set of sticks to the set of jewels. And so, I would say that the set of sticks has the same cardinality as the set of jewels. In addition to my set of sticks and set of jewels, I have a set of coins. Now, I want to check if the set of coins has the same cardinality as the set of jewels. So, let us do that. I pair off each carom coin with a jewel. For this, I do not need to know how many carom coins are there or how many jewels are there, I just need to know that I can pair them up. So, now I have shown that the set of jewels is in bijection with the set of coins. Does this mean that the set of sticks which we saw was in bijection with the set of jewels is also in bijection with the set of coins? Yes, of course, right. So, if the set of sticks has the same cardinality as the set of jewels and the set of jewels has the same cardinality as the set of coins, then the set of sticks must have the same cardinality as the set of coins.